Wow. Okay. That, that is fascinating. Um, do you know if other labs have started buying pasta makers
I
because of
I
this?
I I I I think I know there are other people who do it for other purpose. So yes, there are people who do that.
Yeah.
Yeah.
Okay. Interesting. Has the price of pasta makers gone
Not yet.
up?
No,
like,
we bought very cheap from Amazon. I
yeah.
think it was
Okay.
like $20 or something like that.
Okay.
So
Okay.
not yet.
Yeah. Okay. Hello, everyone. Welcome to the Material Minds podcast, the place where we talk to the people exploring new materials for a better world. Today, we talk with Michael Naguib from Tulane University, all the way from the US. He's the inventor of a new material, of a two-dimensional material, sort of like graphene, but with a much cooler name, MXenes. These materials have incredible conductive and mechanical properties that make them ideal for applications ranging from energy storage to stimulating nerve cells. It was a fascinating conversation. I learned so much from it, and I'm sure you will too. So let's go ahead. So, welcome to Material Minds, Michelle. Or Michael, actually.
Michael,
Right.
yes.
Yes, Michael. Welcome here to Material Minds. It's great to have you on.
Thank you so much for having me.
Yeah, it's wonderful. And you're a guest here at INM at the group of Professor Volker Presser. And you're here in Germany as a Humboldt Research awardee. So yeah, it's a real great pleasure to have you on here.
Oh, the pleasure is mine. I'm very grateful for the Humble Foundation for the award. It's I feel very honored to have it, and grateful for Volker to for having me here and inviting me here. And so I'm excited for it.
So, a lot of excitement
Yeah.
around. We want to get to know you a little bit more. We're going to do that through our usual game of three truths and a lie. So, you've got four statements prepared.
Hmm.
One is a lie. And yeah, I've got to figure out which one that is.
Cool.
So,
Do you mind if I look?
yeah, yeah, absolutely. Have a look. And when you're ready, just go ahead with the
Okay,
first
I'm
statement.
ready for the first one.
All right.
Okay, so um, it is a long statement. Okay.
Mm-hmm.
Um, uh, I was the first of my class was undergrad in metallurgical engineering,
Mm-hmm.
and I have a master in welding metallurgy.
Mm-hmm.
Is it truth or lie, or you can start
Okay,
asking?
this is the statement.
This
So,
is it.
okay. For context, now you're doing nanomaterials, you're doing energy related work, batteries, I guess supercapacitors, these
Yeah,
sort of
and
things.
I work predominantly with ceramics now. I don't do any metals.
Okay, so but undergrad you did welding
Yep,
and you were top of your class.
yep.
Um, Was there an obvious natural transition from that to what you're doing now, or was it just like you had enough of welding, you'd conquered welding, and now you're going to ceramics?
There was no obvious transition. The
Okay.
transition is I wanted to work on advanced materials. I felt,
Mm-hmm.
yes, welding is great and metallurgy is great, but it felt like this is not the. There's lots of research that can be done in advanced material, and I felt, yeah, that's enough with metallurgy and enough was welding. I loved it, but that was
Okay.
abrupt transition.
Okay. So this was in your undergrad, you
Hmm.
said, right? Like your undergrad. Where was it?
Cairo University in
Mm-hmm.
Egypt. It's Faculty of Engineering there, so we
Okay.
had a very well-established metallurgical engineering department there.
Mm-hmm. So it's a bachelor in engineering in metallurgy,
Yes, bachelor and master.
bachelor and master engineering metallurgy. Okay. And you dominated your courses there. You got deep into welding. So at which stage did you make the switch then?
Like right after my master, I so
Okay.
or at during my master, I started looking for PhD in advanced materials.
Okay.
So
And advanced materials brought you to ceramics,
nanomaterials, ceramics, yeah.
nanomaterials. Okay. Are there any concepts, principles, whatever, from the welding studies that you had that you could bring over?
Oh, absolutely, a lot of
Okay.
things. So lots of the fundamentals we learned for from metallurgical engineering we apply easily in other uh, material
Mm-hmm.
systems, phase diagrams, kinetics,
Mm.
physics, lots of things we learned. It's actually easily transferred to other material system beyond metallurgy. So it was not wasted
Okay.
life. I lots of my foundation is based on that, and I still use lots of the things I learned as an undergrad.
Okay. Yeah. Well, and now I assume also you have work with metals, even though it's predominantly ceramics, or is it
No,
not?
not significantly. So
Okay.
most of my works now is nanomaterials and ceramic materials. So
Mm-hmm.
we do work with metals like rarely,
Okay.
but it's mostly nanomaterials and ceramics.
Okay. So that's very interesting to know. It's quite a switch. It's tough for me to know if this is the truth or a lie, but maybe I'll hear your next question or
Okay.
your next statement, and then
Okay. My next statement is inventing a family of 2D material was not the goal of my PhD when I started.
inventing a family of 2D materials is not the goal. Okay. When you started your PhD, or when you
When I
started
started my
your
PhD,
PhD, okay, but you ended up doing that.
I ended up having, yep.
Okay. Can I ask what the goal was?
Yeah, it's actually interesting. The goal was to study the effect of vacancies, atomic vacancies on certain electronic and magnetic properties of layered material.
Okay.
This was the initial, very first project my PhD advisor assigned to me.
Mm-hmm.
That soon after it switched to another project, which was try to use layered transition metal carbides as anode materials for lithium-ion batteries.
Okay. There's a lot of words there that I'm not very familiar
No, I'll be
with.
happy to.
Maybe the first thing, vacancies, when you talk about it, is this like semiconductors
So,
that I understand, or how?
so in material science, we in solid materials, you have atoms arranging themselves into the lattice.
Mm-hmm.
And if an atom is missing from a certain place, this we call this a vacancy.
Yeah.
So and vacancies usually affect electronic properties, magnetic like affects the properties of the materials because they are some sort of defects.
Mm-hmm.
So, but defects can be utilized to tune the material properties, or it can be a disadvantage, and we would like to minimize it.
Mm-hmm.
So, it was not semiconductors; these are layered materials of high electrical conductivity.
Mm.
They are called max phases, and the idea was to study the effect of vacancies in the nitrogen and carbon sites in these layered carbides and nitrides.
Okay.
So it was not semiconductors; it was more on understand structural materials properties.
So okay, while these vacancies affect electronic properties,
Mhm.
you were interested in the structural properties.
In
And
the correlation between structure and property.
okay.
So because vacancies are like you are removing something from the structure, right?
Mm-hmm.
So and studies the correlation between these vacancies and structure and material property after that. So
So is material property like hardness, toughness, this sort of thing, or?
materials properties goes from conductivity
Mm-hmm.
to magnetic behavior,
Yeah.
hardness,
Okay.
hardness as well, tensile.
Mm-hmm.
So all mechanical properties and also physical properties too.
Okay. How are these vacancies created?
Some of them are created by simply during the synthesis, and
Mm-hmm.
uh, some are unavoidable. That there are
Okay.
some vacancies in the materials. It's hard to make a perfect
Okay.
material.
But is it controllable how many vacancies
In
or the
principle,
proportion?
you have certain knobs you can turn,
Mm-hmm.
changing the stoichiometry a little bit by starting with different ratios of the different elements.
Mm-hmm.
You can do some certain treatment, expose it to radiation, expose it to heat.
Mm-hmm.
You can in principle introduce more vacancies in the material.
Okay. Then you talked about these transition metal carbides.
Mhm.
Can you take that step by step a bit? Like, what are transition metals? What are transition metal carbides?
Okay, yeah. So transition metal is simply um, like titanium,
Mm-hmm.
like vanadium, chromium. These are transition metals
Mm-hmm.
in the
It's
periodic
just in
table.
the periodic table, the
Yes.
transition. Yeah.
So yeah, the transition metals in the periodic
Mm-hmm.
tables. Transition metal carbides that are the carbides of these transition metal or nitrides of these
Mm-hmm.
transition metals, and they form this hexagonal structure
Mm-hmm.
that is close packed carbide blocks on top of each others.
Okay.
and they are interleaved with a metal layer, which like aluminum, for example.
Mm-hmm.
Can I show you?
Sure. Yeah.
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 So,
I'd be
for example, here, this can be a transition metal carbide block,
Mm-hmm.
and then we have this gray atoms can be aluminum, for example,
Okay.
that's gluing another transition metal carbide block on top with the one in the bottom.
So what I see here, what is the golden? What are the golden balls? What are the black
So
balls? For
let's
example.
say titanium and carbon and titanium.
Ah. Okay. Yeah.
And so the center or the black atoms can be carbon or nitrogen in the center there.
Mm-hmm.
And the golden here are transition metals.
Yeah.
Similarly, here these can be transition metals,
Mm-hmm.
and the blue can be transition metals, while the black is the
Carbon
carbon nitrogen.
or nitrogen.
And here's the metal layer can be aluminum, gallium,
Mhm.
tin, germanium, silicon, many more. So so these are the max phases. This is how my PhD started. That
Mm-hmm.
I was supposed to make these max phases and create vacancies and study the effects of vacancies in the lattice here in this black atoms.
So the vacancies form in the in that lattice. Of the
Yes,
black
if you take
atoms,
one
yeah.
carbon atom, there's a
Mhm.
vacancy.
Yeah. Okay.
So yeah,
And what is the purpose of the aluminium in the middle?
this is how we make the structure, and it is, in fact, it actually acts like a metal glue
Ah.
between
Okay.
these sheets.
Mhm.
But it really changes the mechanical property of the material. It changes the behavior of the material. So these layered carbides you can machine,
Mm-hmm.
while usually people have the impression that ceramics are very hard to machine.
Okay.
But these you can use a hacksaw and you can cut through
Mm-hmm.
because of these kind of arrangement of atoms.
Okay.
So yeah, so these are the max phase, and I told you the first part was to create vacancies. Second part was in the PhD. Then it turned to be try to use these layered max phases as anodes for lithium-ion batteries.
Mm-hmm.
So
As anodes for lithium-ion batteries. Okay. Sorry, just 1 second. For our viewers or for our listeners who can't see, basically what Michael's holding is like two sandwiches, like two, uh, like a 3D printed, 3D printed structure, which has balls in layers, basically. So the balls are atoms. They're sandwiched two golden layers of balls with a black layer of balls in the middle. The golden layer ones is what he said as titanium. The black ones are carbon. On top of that, there is a layer of gray balls, which is aluminum, and then another sandwich of blue and black.
that can
blue
be also
balls,
transition metal carbide.
which is another transition metal
Yes.
carbide. Yeah. Okay.
So the idea about using these for lithium-ion batteries was this metal layer is known to be good anode materials or high capacity anode materials, like aluminum, silicon. Silicon, for example, has an amazing specific capacity. It's almost an order of magnitude higher than graphite, which we use in our cell phone right now. But the problem of silicon that when it get lithium, it expands too much and it pulverizes.
Okay.
You have more than 300% expansion, so it pulverizes into smaller particles.
Okay.
And this causes very rapid degradation in the performance. So the idea that my PhD advisors, Michel Barsoum and Yuri Gogotsi, had at that time was, okay, you have this metal layer here, it's sandwiched between these transition metal carbide blocks. And transition metal carbides are known to be a good electrical conductor, high mechanical strengths, and high stiffness. So even if this pulverizes, if the metal layer in the middle pulverizes, it is protected by these carbides
Okay.
that can provide the electrical conductivity and
Okay.
mechanical integrity for the electrodes. So it was a very good idea. So it became my PhD topic for quite some time to try to get lithium, go between the layers with metal like aluminum or silicon,
Yeah.
and
Okay.
alloy with them. But I failed.
Okay. But you failed, and then you ended up creating.
Oh, I
2D
failed
materials.
miserably.
Okay.
I spent like 7 months
Uh-huh.
trying and trying and trying, and it didn't work. Lithium doesn't want to go inside.
Yeah.
And actually, interestingly, initially we got some promising results.
Uh-huh.
And but my, as I said, my advisors were writing a proposal and to Department of Energy, and the preliminary results were encouraging. And say, submits a proposal, and I continued working on the project while the proposal under review. And during that time, I proved to myself and proved to them that the preliminary results we were getting were more from impurities in the material, not really from the material itself.
Okay.
So the material has some intermetallic during the synthesis, and this intermetallic is what giving us the capacity.
Mm-hmm.
And lithium is not going between the layers. So, okay, lithium is not going between the layers.
Mm-hmm.
And then what should we do? We tried multiple strategies. One of them was try to reduce the particle size significantly. And this is a known strategy in silicon, for example. I mentioned silicon earlier, that silicon start to have good performance when you are in the nanoscale. So, okay, let's try to grind and mill these bulky max phase ceramics into smaller particles. We tried that. Didn't enhance the performance.
Okay.
The other idea was, okay, what about creating some vacancies? But this time, the vacancies, we want to create them at the metal layer here, in the aluminum, for example.
Yeah.
So to remove some so we can allow lithium to go inside. So started by creating some vacancies and still didn't work.
Okay.
Then I went to my advisor and said, okay, what about removing the A layer completely out?
Uh-huh.
And I have to tell you, I was struggling to create vacancies.
Yeah.
Then one of them told me, you're struggling to create vacancies. You want to remove it completely? And then he laughed and, yeah, sure, be my guest, try.
Uh-huh.
So then I decided to try, and I tried, and I removed this metal layer completely out of the structure.
Uh-huh.
And now you had this metal glue between the layers. Now it doesn't exist anymore. So now we have a more of a hydrogen and van der Waals interaction, because we replace transition metal surface cannot stay bare. So usually they would get surface terminations on top.
Ah, okay. So things start reacting with it, and
With the waters that we do this in water
okay.
and in an acidic system, an aqueous system. So they start to get terminations here on the top of the transition metal surface, like hydroxyl termination or oxygen termination or fluorine termination. And then you can easily separate the layers from each other. Now you end up by these 2D blocks as sheets and standalone sheets, and you can have them in colloidal dispersion.
Okay.
And that's how MXene became a family of materials.
Okay. Okay, so that's how the MXenes were invented.
Yes.
Back then. But you did, yeah, okay. So you didn't start out with this plan.
No, not at all.
Okay. I'll have to think about this one.
Okay.
Yeah, of course. Let's go on to your third statement.
Okay, my third statement is MXenes can replace all other 2D materials, including graphene.
Wow. Okay, that's a big one.
It's a bold statement.
That's a bold statement. Yeah. Of course, you've invented it. So I've heard a bit about MXenes, but can you justify the statement? So why do you think that's the case?
Okay, so MXenes is a really large family of materials.
Mm-hmm.
So far, there are more than 50 different compositions of MXenes.
Mm-hmm.
And in materials, when you change the composition, you are changing properties. You are changing the behavior of the materials.
Mm-hmm.
So you can have MXenes semiconductors, MXene metallic with conductivity comparable to graphene.
Mm-hmm.
You can have MXenes that are hydrophilic. You can have MXenes that are hydrophobic. You can have MXene that have high thermal conductivity. You have MXene that has poor thermal conductivity. You can tune their properties as much as you want.
So is this based on the vacancies, or is it based on the metals that you select, the transition metals?
Based on all of the above. Based on you can create ordered vacancies in these MXenes. Something that's very hard to do in other layered materials, that order defects. Defects are there. There's always defects in material. Unless you work very hard to minimize them. But in MXenes, we can make ordered vacancies.
Okay.
You can change the transition metal. You can change the X, or you can have carbon or nitrogen. You can have different transition metal as these blue atoms can be titanium, niobium, molybdenum, vanadium. So we're talking about huge compositional space that you can tune by simple changing chemistry, by also changing structure slightly. So in this model, it is just one block of transition metal carbides. we can make MXenes with actually the single layer become double block or triple block or quadruple blocks
Mm-hmm.
of these transition metal carbides. So you can change the thickness of the single layer of MXene.
Okay.
You can, as I mentioned, create vacants. You can have certain transition metal outside and another transition metal inside. Molybdenum outside and titanium is
Okay.
a core. So we're talking about huge compositional space that offers tunability that no other 2D materials can. So in principle, you can
Mm-hmm.
tune the property based on the application you need at the end,
Mm-hmm.
and by changing composition, introducing defects, changing thickness, all of this can lead to property you need, so you can replace all others. And they are
Okay.
very easy to make.
Yeah, that was one question I had. But okay, I have actually a couple of very basic questions before that. One, the name MXene. You
Oh.
talked about max phase materials and you talked about graphene a bit. So is this a combination of these
It's
two?
exactly it is.
Okay.
So yes, so in max phase, if you remember, I was talking earlier that we had this metal layers
Mm-hmm.
between the sheets. So we remove this metal layer, so it become MX, not MAX. So
Okay.
so they're
Okay.
called max phases. M is like transition metal. A is A layer
Mm-hmm.
metal layer, and X is carbon or nitrogen. So we
Mm.
remove the A out, so it become MX,
Yeah.
and we put the suffix "ene" to stress similarity to graphene.
Yeah.
Uh,
Okay.
yeah, so just some analogy or some similarity to graphene.
Yeah.
Electrical conductivity, I mentioned this to you,
Mm-hmm.
is one of those very. It's only MXenes that can have comparable conductivity to graphene.
Okay.
Yeah, so this is where the name came from.
Okay. And another very basic question is, does it have to be only transition metals in these layers, and why?
So far, yes. So thermodynamically, they are the way we make them is solid state synthesis or powder metallurgy.
Mm-hmm.
So we mix elements together and then we heat them to a certain temperature.
Mm-hmm.
And so far, the transition metal carbides are the ones that, or nitrides, are the ones that can make the structure
Mm-hmm.
of blocks of metal carbide interleaved with a metal layer.
Okay.
Um, so this is so far what we have been doing, and this is thermodynamically transition metal are needed for that purpose.
Okay.
They stabilize the structure. The structure can be stable that way.
Okay.
Um, what was the other question?
So no, that was the main
Yeah.
question. Yeah, basically. Then coming back to what you had been talking about, so the applications you say for, so 2D materials have many applications. So you have I don't know, your smartphone screens, for example, or you know, big large screen TVs related things, conductivity related things. So capacitors, of course, and yeah, electrodes in batteries and so on. So are you saying that basically this, you've already, I think, justified quite a bit that you can get a lot of properties out of it, whatever you want, pretty much. So you're saying that these can be produced easily enough, cheaply enough, and with the properties that you desire to cover this large spectrum of applications.
Yeah, so this is relative to other 2D materials, other nanomaterials in general.
Mm-hmm.
The way we prepare these materials is very scalable and very easy to do in the lab.
Okay.
So even very early on, we could make batches of 30 grams. And when we talk to nanomaterial people who say, I make 30 grams, they look like surprised.
Yeah.
What are you talking about? This is huge. Actually, in fact, now kilograms quantity can be made, and there are companies licensed in Japan and England and many places that they are actually producing them in large quantities. And
Okay.
some companies already sell it, so you can buy MXene commercially now available. So scaling up or producing a large quantity and simplicity of the scaling up make it relatively easy to prepare material
Mm-hmm.
compared to other exotic nanomaterials.
Mm-hmm. Yeah, and for me, these are sheets, right? Like if I think of graphene with this also, so is it also possible? How big are these sheets that you can make, and how much control do you have over that?
This is a very good question. Actually, it is challenging.
Mm-hmm.
So the way we are making them at the moment, we start with from the max phase, and then we selectively remove this metal layer out.
Mm.
And the size of the max phase you start with is a limiting factor for the size of the MXene. You cannot make the MXene larger than the max phase. Sure, you can play with self-assembly and can achieve thin films that are as large as you want, but these thin films consist of smaller flakes next to each
Mm.
other and laying next to each other. And yes, this is done. People make wafers,
Mm-hmm.
large wafers, well, using MXenes and
Mm-hmm.
in a very rapid
What is
pace.
large?
Um, 5-inch wafers
Okay.
and larger.
Okay.
So people can make
Yeah.
and actually you can make in our lab we make freestanding MXene paper, which is paper a few micron
Yeah.
thin
Mm-hmm.
of restacked sheets on top of each other.
Mm-hmm.
We make an A4 size
Yeah.
in the lab. We do this routinely, and there are people who are reported meters long films of
Whoa.
MXenes that are
Okay.
few micron thin.
Uh-huh.
So you can play with thin film preparation using MXene colloidal dispersion because we make them easily in water,
Mm-hmm.
which is another also interesting thing that
Yeah.
2D materials you cannot process them in water, but we
Mm-hmm.
make these. We exfoliate them in water, and you have this black ink
Mm-hmm.
that you can do any additive manufacturing techniques
Mm-hmm.
to turn them into films or 3D architecture, whatever you want to do. So, but each flake, as I said, is limited by the size of the max phase. So
Mm-hmm.
we're talking usually in the microns range lateral dimension. So the thickness
Yeah.
is sub-nanometer,
Mm-hmm.
but the lateral dimension of each flake is in the microns, few micron, sub-micron range.
Okay.
You can intentionally try to make them make the max phase larger.
Mm-hmm.
20 micron, 30 micron, 40 micron, but it's usually harder to make them very
Mhm.
large. So make them smaller, it's easier to
Yeah.
bring them down.
Okay. So then if they form the micron range and then you make them into films of
Mhm.
whatever size, do they have any properties to align like in a 2D phase, or would they kind of overlap over each other? Would they stick in different directions and so on?
You can, it actually depends on the application you want. For
Mhm.
certain application, you would like them to be randomly distributed.
Okay.
So you have easy access of ions.
Like which? Oh, like with the
For
batteries
energy
and stuff?
storage, for
Yeah.
example,
Mhm.
restacking them like very perfectly on top of each other is actually
Mhm.
terrible because ions cannot penetrate.
Yeah.
easily
Okay.
there.
Mm-hmm.
So you would like them to be more randomly stacked so ions can diffuse and
Yeah. Okay.
then run through easily.
Mm-hmm.
Um, but for other applications, you would like to minimize defects
Mm-hmm.
and you'd like to have more of a perfect alignment of atoms, of layers.
Yeah.
And you can do that playing
Uh-huh.
with surface chemistry and some tricks in
Okay.
how you prepare the film on top of water, for example, and then you move this
Okay.
film away from the water. So you can play with surface chemistry and colloidal dispersion, and you can manage to make semi-perfect or minimum defects, minimum pinholes
Mm-hmm.
between the sheets.
With comparable precision as with graphene and so on.
Graphene, if it is produced from liquid exfoliation,
Mm-hmm.
yes,
Mm-hmm.
MXene can even, similar quality.
Mm-hmm.
But one thing graphene has that MXene doesn't have yet is you can produce graphene with chemical vapor deposition.
Mm.
You can make roll-to-roll production
Yeah. Okay.
of graphene
Mm-hmm.
in meter length with chemical vapor deposition. MXene is not there yet.
Not there yet, is what
Yes.
you say.
Yes.
Which means there is something in development.
I believe it will not be in the far future until MXene. So
Okay.
something will come with MXene or MXene-like produced from CVD. There's already some reports on attempts to do chemical vapor deposition and to use chemical vapor deposition to make MXene. It didn't end up in making films. It ended up to make more of flakes or 3D architectures
okay.
of MXenes. But I believe it is with some more precise control and some more conscious design, you can, in principle, get to
Okay.
that stage.
Okay. One last question about this point also for me is the other big 2D material that I know of is graphene, and graphene is used for biological applications also. What are the kind of biological applications you see with MXenes?
It's actually fascinating that MXene actually quite recently, in the last few years, have attracted the attention of the biomedical, bioengineering community, and
Mm-hmm.
very impressive performance. MXene offers this excellent electrical conductivity,
Mm-hmm.
which graphene can too as well.
Mm-hmm.
So you have to be fair. So
Yeah.
MXene is second to graphene in terms of electrical conductivity. There is no
Mm-hmm.
other materials as good in 2D. But graphene is very simple.
Mm-hmm.
It's just carbon.
Mm-hmm.
So functionalizing the graphene is a challenging task.
Mm.
So in terms of MXene, you can functionalize the surface. The surface is functionalized
Yeah.
as
Mm-hmm.
you make them, and you can play with that, and you can anchor different things on the surface. You can anchor a drug, you can anchor
Mm-hmm.
surface moiety or surface functionalities that can do certain thing.
Mm-hmm.
So this kind of tunable interface with MXene makes it interesting. When we talk about there's some application as using MXene as interface with some neurological
Mm-hmm.
applications, or
Yeah, yeah.
so because they are good electrical conductors,
Uh-huh.
so they reduce significantly the resistance, and since they get a very faster and cleaner signal
Yeah.
by using MXene instead of the conductive paste they add
Mm-hmm.
or conductive glue they use.
Yeah, yeah.
So MXene outperforms it significantly. And
Nice.
there's great work published in this direction. Another direction is some of the therapeutic using MXene as you know about gold nanoparticles for
Mm-hmm.
treating cancer and things by shining light at them.
Yeah.
MXene actually can outperform gold for this application.
Okay.
Certain MXene, because initially I told you we have large number of compositions.
Mm-hmm.
So tantalum, for example, outperformed titanium in this application.
Yeah.
So antibacterial applications as well. We're talking some interesting application using MXene for dialysis
Mm-hmm.
to remove urea from bloodstream, and actually showing very interesting performance. And there's a startup company that's working on that.
Yeah.
So there are more and more biomedical applications for MXene that are appearing, and where MXene is actually outperforming many of the well-known materials.
That is fascinating. Okay. So I think you've justified it quite extensively, and the third statement sounds pretty solid right now. Let's listen to your fourth statement. And then I can
This is my
try to
last one,
guess.
right?
Yeah.
Okay, yeah. In my lab, we use pasta maker regularly for research.
Ooh. Like to make lasagna plate kind of layers? Or
We use it. I can tell you how
Okay.
we use it. We
Yeah.
can't make lasagna,
uh-huh.
but we use pasta maker.
Okay, no, this I'm very curious about. So
Okay.
so how does that get used?
Okay, so recently in my lab, we developed a new family of transition metal
Mm-hmm.
carbochalcogonides, where
Okay.
they have the core of MXene, but the
Uh-huh.
surface is a chalcogon, is sulfur or selenium or tellurium.
Okay.
So and we make these materials by solid state synthesis. We don't need to, in case of the max phase, we remember we
Yeah.
had this metal layers that we have to etch out. So we make the max phase by solid state synthesis. Then we use wet chemistry to remove this out.
Yeah.
Then we exfoliate these sheets.
Uh-huh.
For transition metal carbochalcogonides that we developed recently in my lab, we actually make these directly, the transition
Okay.
carbochalcogonide directly
Uh-huh.
by solid state synthesis.
Okay.
And the surface here has chalcogon, like sulfur or selenium or tellurium.
Okay.
And
uh-huh.
so, and the interaction between the layers is van der Waal interaction. So we make them by solid state synthesis. We can make large quantities. We can make them rapidly in terms of minutes. And then to separate these layers from each other, we introduced lithium between the layers
Mm-hmm.
to space them away from each other.
Okay.
And then we take it and throw it in water.
Uh-huh.
Lithium reacts aggressively with water,
Uh-huh.
form lithium hydroxide, that's
Yeah.
water soluble, and
Yeah.
hydrogen that
Uh-huh.
pops open
Ah.
the layers. Then we
Okay.
end up by a nice colloidal dispersion.
Yeah.
So initially, in our first paper published in Advanced Material in 2022, we introduced the lithium between the layers electrochemically.
Okay.
We in our group we do energy storage, electrochemical energy storage. So we make a battery of our material, put the lithium electrochemically between the layers, and then take the electrodes out, rinse it with a solvent, and then throw it in water and do the exfoliation,
Mm-hmm.
and we showed it works and everything's nice. But I don't. It give you small amount of material
Yeah, okay.
because the battery you are limited with the electrode size,
Mm-hmm.
and it takes long time to discharge or introduce the lithium between the layers. So I didn't like that.
Mm-hmm.
I asked my students, let's introduce the lithium mechanically.
Okay.
So people do mechanical alloying all the time.
Uh-huh. Okay.
So why don't we?
Mm-hmm.
So mechanical alloying people do milling
Uh-huh.
for two different metals together, and this milling, the high energy of the mill,
Mm-hmm.
introduce diffusion or help facilitated diffusion and help making the alloy.
Mm-hmm.
So the same idea. Let's mill lithium powder with our material,
Mm-hmm.
and then this way we can use grams quantity rather than the small amount
Yeah,
of the
okay.
electrode material. So this was the idea I suggested to my students. We tried. People sell lithium powder, stabilized lithium powder, but there are there are lots of safety regulations in handling these
Uh-huh.
lithium powder, and we were trying to buy them. It was taking us forever for some bureaucracy on both sides. So at some point, my student got tired of waiting and said, "Okay, I'm going to try milling. Rolling.
Uh-huh.
It's another source of mechanical alloying, as we can roll things together." So he went to the lab and rolled lithium foil,
Uh-huh.
and then put the powder, sprinkle the powder on top of the lithium, fold the lithium, and roll again, and
Okay.
then repeat the step multiple times, and then throw it in the water like I was suggesting
Uh-huh.
for the milling. And it did work. And he
Okay.
came to me, said, "Okay, I managed to exfoliate them, and
Uh-huh.
here's a colloidal dispersion. This is very exciting." And I was super excited, and I asked, "You know what? I always would like to make sure things are reproducible. So
Uh-huh.
let's ask another student to do it."
Uh-huh.
I asked the other student to do it. She went to the lab and she came back. It did work, but I didn't get as much material as what he got.
Uh-huh.
Then I thought, okay, I think I know why.
Uh-huh.
Because in the rolling, it depends if you ate your breakfast or not, or
Okay.
if you feel good, you are
Yeah.
strong, or you are tired from the gym, whatever. So it can be variable from one person to the other.
Uh-huh.
So I said, okay, instead of depending on our hands, let's get a pasta maker,
Okay.
put it in the glove box,
Uh-huh.
and for the rolling,
Yeah.
instead of do it with your hand, you do use the pasta maker, and this way we have reproducible results,
Yeah.
regardless of who is doing it
Yeah.
and what time of the day you are doing it. And we have it now, and it's working beautifully, and we produce tens of grams of these
Okay.
materials very rapidly.
Wow. Okay. That that is fascinating. Do you know if other labs have started buying pasta makers because of this?
I think I know there are other people who do it for other purpose. So yes, there are people who do
Yeah. Okay. Interesting. Has the price of pasta makers gone
it.
up?
No,
Like,
we bought very cheap from Amazon.
yeah.
I think it was
Okay.
like $20 or something like
Okay.
that. So
Okay.
not yet.
Yeah. Okay. Oh, that's wonderful. Yeah. Yeah, you got four statements that are very tough for me to figure out if which one's a lie.
Okay, good job, me.
Huh? Yeah, yeah. Let me recap a little bit. So the first one is that your undergrad was in metallurgy, doing welding,
Mhm.
particularly. I see hints of it in what you said in the other statements, with different layers and so on. I could believe that, I guess. The second one is you didn't start out your PhD with the plan to invent this beautiful MXenes or a new type of 2D material, which I could believe largely because often PhDs don't start and end the same way, or they don't end the way you expected when you started. Okay. The third one is the one I'm most leaning towards. It's the biggest statement, or let's say the most bombastic statement,
Mhm.
I guess, of them all, that MXenes can replace all 2D materials, but you justified it quite extensively. And the fourth one is use the pasta maker, which I want to believe so bad. So I'm going to challenge your third statement.
You are correct.
I'm correct?
You are absolutely correct. Yes.
Ah,
So
okay.
while I love MXene, it's fantastic
Mm-hmm.
material. It offers a wide range of properties and applications. Actually, even just wanting it to replace all is not wise. It's wide.
Mm,
It's actually it's good to fill gaps
Mm-hmm.
in knowledge or fill gaps where other 2D materials cannot perform well.
Mm-hmm.
For example, I mentioned to you MXene being hydrophilic
Mm-hmm.
and being good electrical conductor.
Mm-hmm.
This combination of properties is very rare.
Yeah.
So graphene is hydrophobic, or at least multi-layer graphene is hydrophobic,
Mm-hmm.
good electrical conductor. So while clays, which is the most ancient and most studied layered material,
Mm-hmm.
very good hydrophilic material, but
Mm.
insulator or semiconductor with large band gap.
Mm.
So we have these combination of properties that's rare. So it's better to think of MXene as it complement other 2D materials where they cannot perform, but replacing all, I think it's not wise even to think in that direction. So,
Okay. Okay.
so
Well,
yeah,
that's
good guess.
that I'm happy.
And
It
we
was
do use pasta makers. This is 100%
yeah. This
true.
I'm so happy that's true. I'm so happy that's true. Well, I was rooting for the third one also because I've heard so much about MXenes, but and the fact that you said how easy it is to make them and how many properties you can build into them, how you can apply them for biology also because I have a biology background. But I completely agree with your justification now that it actually you don't need to. I mean, this is not a goal that you need to achieve. It does amazing things, and yeah, it stands on its own in what it can do. So yeah, that's incredible, and yeah, it was purely a guess, of course, but the pasta
Good
maker
one.
one I love. Yeah. Oh, that's wonderful. All right, so usually around this time I get to the point where I ask what's your favorite material, which is
I guess you know it.
I think I have a clue. Yeah. Although I could ask you, you talked about the newer ones that you're making with the pasta maker now. Are MXenes still your favorite, or are these ones also a type of MXene, or not?
It's a very valid question. So one can think of these as MXenes with sulfur, selenium, or tellurium termination,
Mm-hmm.
and this would be completely fine.
Mm-hmm.
They are not made the same way MXenes are made,
Mm-hmm.
and to make MXenes with sulfur, selenium, or tellurium, it's very hard. It's doable,
Okay.
but it's very hard.
Mm-hmm.
So, in principle, you can go from traditional MXene with oxygen hydroxyl termination to TMCCs or transition metal carboxyl or you can go from transition metal carboxyl to MXenes, and this is what we are trying to do actually in full course lab
Okay.
here.
Uh-huh.
So, in principle, this kind of switch is doable. So, I'm fine if we think about them as MXenes with sulfur selenium termination, or think of them as standalone. In the literature, we were not the first to make these transition metal carboxyl a multi-layer
Uh-huh.
material, carbosulfides they call them. We were not the first to make them. They were
Yeah,
first
okay.
made in 1970,
Okay.
but they were never explored as 2D materials. No one
Yeah.
tried to exfoliate them.
Mm-hmm.
So, and they were called carbosulfides. So we stick with the name carbochalcobunide, or because we
Okay.
can make selenium as well, not just sulfur.
Mm-hmm.
So can they be better than MXene? The way we make them is much easier than the way we make MXene.
Mm-hmm.
So this gives them an advantage. However, compositional wise, we are still in the beginning. So MXene now there are, as I said, 50 different compositions.
Yeah. Okay.
While for these, we maybe have made like 7, 8 compositions. So
Okay.
we're still very far from
Yeah.
comparing to MXene.
Okay.
And as I said earlier, we don't need to compare to MXene. It's by themselves they are interesting. The way we make them is very scalable, much more scalable, easier to scale up compared to even MXene. So there are certain advantages in them, and we are still trying to understand more.
Okay. Then maybe I'll twist my question a little bit this way. For your favorite material, which is your favorite MXene?
Oh, it's
Do you have one? And
Oh.
which is
it's my favorite because it was the first we made. It's titanium 3C2, titanium
Okay.
carbide MXene.
uh-huh.
It's my favorite because it was the first I made in the lab, and I made it almost by accident.
Okay.
So and it is the most studied one.
Mm.
It is easiest to make
Mm-hmm.
somehow,
Mm-hmm.
and it is the most studied, like thousands of papers published on TI3C2,
Mm-hmm.
which makes it less interesting to study because
Yeah.
it's well studied.
Yeah. Yeah.
So it is my favorite because it's the first, but I don't work much with it.
Okay.
because there are other compositions. Molybdenum is very interesting. Molybdenum
Yeah.
carbide
Okay.
MXene is very interesting because you can create these ordered vacancies in it. Yes,
Mhm.
and niobium carbide MXene is interesting. Vanadium carbide MXene is interesting. Carbonitrides are very interesting
Mhm.
to me. So it is my favorite because the first, but it is becoming boring because it's well studied.
Yeah. Okay.
So
Okay. So then, you talked a little bit about like different applications
Mhm.
of these vaccines. What are the applications you're particularly focused on?
So in my group is novel energy material. So
Mhm.
MXene and other 2D materials, main applications we look at in my lab is electrochemical energy storage, like batteries, beyond lithium-ion battery, sodium-ion battery, lithium sulfur, supercapacitors. Um, these are energy storage
Mhm.
systems. Also electrocatalysis,
Mhm.
revolution reaction, or green
Yeah.
hydrogen,
Mhm.
using our materials as catalyst,
Mhm.
replacing platinum. Platinum and platinum group metals are very well efficient catalyst, but they are very expensive as
Yeah.
well. So our materials have some catalytic activity,
Mhm.
not as good as platinum, but they
Mhm.
are not platinum.
Yeah.
So
But you save the cost by
significantly.
yeah.
So this is an area of research we are looking into in my
Mhm.
lab, is to make electrolysis more affordable and cheaper.
Mhm.
Um, Another direction we are working on right now, which is funded by the Department of Energy, is using MXenes as sorbent for radioactive iodine. It's an application that
Okay.
I never thought of before until one of my colleagues at Clemson University reached out to me and said, "Would you be interested in using your material?"
Mhm.
Said, "Yeah, sure. It actually might work because
Mhm.
you can have iodine at the surface of MXene. So,
Mhm.
and then this would, if it absorb it, then we're talking about larger capacity.
Okay.
So the idea is in a nuclear reactor.
Ah.
Have you watched Chernobyl?
Sorry?
Have you watched Chernobyl,
No, I haven't.
the
It's,
HBO series?
no, no.
It's a
Yeah.
very fun.
Okay.
It's like exciting to watch.
Uh-huh.
Sad experience, sure,
Yeah.
but
Mhm.
talking about the series itself is
Yeah. I've heard about it. Yeah.
well prepared.
Mhm.
Whenever there's a nuclear disaster, they distribute potassium iodide tablets
Okay.
to people to take
Ah, okay.
because air would be full of radioactive iodine and your body would tend to absorb it. So they saturate your
Ah,
body with iodine that's not radioactive, so your body would not absorb the radioactive one.
okay.
I'm saying that just to say radioactive iodine is one of the byproducts
Mhm.
that you can have in case of a nuclear disaster. Hopefully, never happens.
Mhm.
But also during processing of the fuels later on and recycling, you would have some of these radioactive iodine. And there is a need to absorb this from
Hmm.
the air. Right now, silver is used as
Mm.
sorbent for
Okay.
that. And we have published paper recently on using MXene silver hybrid and showed outstanding iodine uptake. Another work we show recently, but we haven't published yet, that we show the MXene itself can work and can even outperform silver.
Okay.
So, but it's still work in progress. So, wide range of application, but also
Yeah.
we are very lucky to have wide network of collaborators who would like to work with us and
Mhm.
explore some of the new materials we make for different applications. So, for example, I have here Professor
Mhm.
Volker Presser at INM, looking at using MXene for water desalination, for example.
Mhm.
And we're getting interesting results here. And looking for some biomedical application with collaborators in Poland and collaborators in Qatar for environmental application, collaborators in different and in Louisiana Tech for biomedical application. So we have a broad
Mhm.
network of collaborators looking at application beyond what we can do in my lab.
Yeah, and that's a testament to what all you can do with this, right? Like that so
It
many
is
people are
fascinating.
excited to pick it up
It
and
is.
that they're able to make it relatively easily, or you're able to make it and send it to them, I guess,
Yeah.
and they're able to use it quite
Yes.
easily.
Yeah.
So the applicability is fantastic. And that actually basically brings me to the last part of this whole thing. The Federal Ministry for Education and Research in Germany, so the BMBF, their topic, Science of Year of Science topic this year is future energy, which is very kind of related to your work. So, assuming all these, all this research, all this development works beautifully, where do you see in 10 years or 20 years or sometime in the future, where do you see the future of energy? going?
Yeah, it's a very good question, and I'm glad that they have energy as future energy as the topic of the year. It's actually it needs to be the topic of the year every year because how important critical energy is.
Mm-hmm.
Um, I see us moving. So lithium-ion battery, which is predominant energy storage right now, is maturing, and companies produce them in large quantities and megawatt and then gigawatt factory and all of that.
Mm-hmm.
So lithium is maturing. Um, Eventually, we'll get to the point where lithium becomes critical material.
Mm-hmm.
Maybe we are there already now.
Mm-hmm.
And if electrification of vehicles and everything around us continues the same pace, this will become a real challenge.
Mm.
There will be a need for beyond lithium.
Mm.
Um, I am a big believer in sodium as
Mm-hmm.
because sodium, if you look at the periodic table, is just right below lithium.
Mm-hmm.
You compromise a little bit with sodium in terms of the energy density.
Mm-hmm.
Lithium is the highest
Yep.
by far,
Yeah.
but sodium you can you compromise a little bit, but not significantly.
Mm-hmm.
And also sodium in industries they don't like abrupt change in the technology.
Mm-hmm.
So they would like something that can fit nicely in the roll-to-roll
Yeah.
production.
Yeah.
So battery companies can simply replace lithium by sodium by replacing the materials they're using.
Okay.
So I can see that easy adjustment.
Uh-huh.
It's not like a significant. You don't need to rebuild every single factory to be
Yeah.
able to process the sodium-ion batteries.
And sodium is everywhere.
And sodium is everywhere.
Yeah.
Yes, the oceans are full of
Yeah.
sodium, and it's not. I can't see it becoming a scarce material.
Yeah.
So this is, I believe, in terms of the energy storage, and energy storage is really critical, not only for um, electrification, but
Mhm.
also if you would like to use renewable energy in general.
Mm.
You have this gap between demand and supply. You have a sunny day, so your photovoltaics are producing lots of electricity, but in the night, you need to use that electricity. So you would need to have energy storage to use it.
Mm-hmm.
Now you have a windy day and you want to store this energy to the hot day so you can use the AC.
Mm-hmm.
So you need these energy storage, so not only for electrification and mobile movement, but more also for bridging gap between demand and supply.
Mm-hmm.
So making more energy storage affordable and scalable would continue to become a topic for the future. So beyond lithium, also for existing lithium recovery, which is a topic I know Professor Purser here is working on as well. It's a very hot topic and very important topic to be able to recycle the battery, to be able to recover lithium from water streams and things like that. So that will become more and more important. So it's in terms of the energy. Um, Future for our materials or for our research in general, I'm imagining an AI autonomous lab where you have a certain application in mind, certain property in mind, and we have this big library of inks of different compositions or different materials. You build them together with the right ratio you want. They give you the exact property you want, and the robot prepares this for you and give you the material. This is what I'm
Mm-hmm.
imagining in the future for us.
That's beautiful. Yeah. So there's so much reliability in the material, so much width in the application space that you could have basically a well-trained robotic system that can make the material of our desires in the future.
Yeah, I think so.
Wonderful. That's a really great ending message for the episode. Thanks a lot,
you.
Michael, for this wonderful conversation. I learned a whole lot in this whole time. The model helped really a lot for sure.
And you caught the lie.
And I caught the lie.
Yeah.
Of course, there's a huge portion of luck in these guesses, but yeah, all the statements were beautifully crafted, and I enjoyed the conversation around.
Thank you so much for having me.
Yeah, thank you for being here. And thank you everyone for watching. Thank you everyone for listening. We are on YouTube, Spotify, on several different places. Follow us, subscribe, and yeah, watch out for the next one. See you.
Bye.